Well, as also, people will keep trickling in, but and so good afternoon, everybody. Welcome to our LIDS seminar. We are really pleased to have finally we have Dan agree to speak in LIDS seminar. We managed to get him this Zoom pandemic time. But so many of you are probably familiar with the kinds of stuff Dan does. He's well-known figure, in computer science, mathematics, and also data science. And he's actually professor of all three at Yale. And I'm familiar with some fractions of Dan's work, the ones like related to Laplacians, and of course, my personal favorite bias towards Cardisan-Singer business, which I still am reading all the time. But anyhow, Dan has, if you look at his biography, if you don't know Dan, I encourage you to check his webpage out. He's always doing cool stuff. He has long string of recognition starting from his ACM doctoral dissertation award back in the day to so many prizes. Let's see, maybe the information theory paper award, Gödel Prize, Fulkerson Prize, Nevolina Prize, and also I guess this one I don't know is the most latest one probably is the National Academy of Sciences award or medal, and so on. I mean, I think the cool thing is, from what I know, Dan, being familiar with your work, the originality of thinking and ideas and the interplay of different mathematical topics that Dan brings out in his work is just phenomenal and inspirational, which is why I'm very happy, along with the rest of the LIDS audience here, to have him speak about something yet new today. So Dan, the floor is yours, and thanks for joining us.
Okay, thank you very much for inviting me and for the generous introduction. Let's see. Oh, good. I believe I'm sharing screen now. And,
Yeah.
It's wonderful to give a talk at LIDS because I can't, well, one, it's sort of like being home. Two, I'm giving a talk to such an amazing audience. And in the COVID era, I don't even have to suffer regret. I know that I can come back to MIT a few months from now and give a talk, maybe in another department, to an equally amazing and probably disjoint audience. So I'll get to have both experiences. Today, I'm going to tell you about work from a paper called Balancing Covariates in Randomized Experiments Using the Gram-Schmidt Walk. It is joint work with Chris Harshaw, who's a graduate student of mine who'll be finishing next year, Frederick Xavier, who's a professor in political science at Yale, and Peng Zhang, who's a postdoc working with me, who's on the job market right now. In order to save time, I am going to skip most historical references in this talk. So if you want to look them up, we have a very long history section in the paper that I recommend. There is one I really do have to call out, though. That is the Gram-Schmidt walk. The Gram-Schmidt walk is an amazing algorithm that came from this paper, The Gram-Schmidt Walk, A Cure for the Banachik Blues, by Bansal, Dadouche, Garg, and Lovett. And when I finally tell you about this algorithm, you are going to wonder, why the heck did anyone come up with this algorithm? And the reason is to come up with an algorithmic solution to something called Banachik's problem, which I'm not going to get to describe because it doesn't really fit into the talk, but I certainly recommend looking it up to understand what motivated them to come up with this remarkable algorithm. So to explain what I'm doing, I want to put you in my mindset 4 years ago, which is when I started thinking about randomized controlled trials. A colleague of mine, Nicholas Christakis, came into my office because he had a problem. He was working to set up a test of interventions to improve maternal health outcomes in rural villages. They were doing this in Honduras. They were trying 16 different treatments. So 16 different interventions, mainly think about how do you get people, how do you intervene using the social network of a village to get people to uptake new behaviors. But there are only so many villages to work with. They had 176 villages, which is a lot. But with 16 treatments, that meant there were only going to be 11 villages per group. And if if you look at this data, you will see if you look at it carefully enough. For example, here's one of the groups. It's all on the western end of the country. That concerned them because if that is the group that does the best, then, they don't know, is that because of the treatment or something going on the western end of the country? Similarly, here's a random group. One of these groups, and it sort of lies near the middle. That also seemed bad. Now, of course, there are ways of dealing with this problem. Imagine for now, you were just trying to divide the villages into two groups. A standard way to set up trials is you do matching. That is, you start pairing them off into pairs. I hope, let's see, you can see these lines. Well, okay, I don't have a nearby one for that, so maybe it should go here. You start dividing them into pairs. And then for each pair, you say, well, okay, this village, I'll flip a coin. Either say I assign this to group A and that to group B, or maybe for this one, I flip a coin. If it comes up the other way, I assign this to group B and that to group A. If we were only doing 2 treatment groups, that is one of the go-to methods. Okay, but they had 16 treatment groups. As you can imagine, there's a generalization of this. It's called blocking. What you would do is divide these villages into groups of 16. I don't know if that's exactly 16. Maybe here's another group of 16. And then within each group, you do a random choice. Like you'd say, okay, at random, I'm going to assign this to group A, that to group B, this to group C, that to group E, that to group F, etc. So you could try something like that. That's actually what they were doing. And still the results looked unsatisfying. Geographically, they didn't look very nice, but there were bigger problems, which is this is not all they knew about the villages. They knew a lot about these villages in their study. Just to fix terminology, because I wasn't familiar with the word when I got into this, they call things they measure about the subject in the study the covariates. And in this cases, there were many covariates that they thought might be correlated with the outcomes of the study and with maternal health outcomes. Things like the distance to the hospital, how long it took to reach the hospital when it was raining, which could vary quite a bit from when it wasn't raining. Median income in villages, average age of people in villages, what's the percentage of women in the village, of females, the altitude, that varies a lot in Honduras, various social network measures. They had all sorts of things they'd measured about these villages. And once you measure these covariates, you discover that there are no good matches. Once you know enough about people, no 2 of them look the same. Same thing going on here. Once you measure enough covariates, you can't even find good matches, let alone blocks of villages that look similar. So they needed something else. Now, my first thought was, okay, I know I can at least give them something good for this because I'd spent some time studying discrepancy theory, which is largely about how do you divide up a bunch of things into groups so that each group looks similar. And we do know you can do much better than random. And I did have some code for this from my work on the Caddison-Singer problem. So we leveraged that code to try to come up with a solution, or that's what I thought we were going to do. But then I discovered the problem wasn't exactly what I thought it was. It wasn't really just to divide the villages into groups. They didn't want one assignment of villages to treatments. They wanted a distribution on assignments. Meaning, I wanted to take this problem and treat it as an optimization problem, and they convinced me this is not an optimization problem. The reason they want, say, a distribution on assignments is at the end of the day, they want to do things like compute p-values or confidence intervals. And to do that, you need something random going on, and that is the distribution of how you are going to assign villages to treatments. And what you get from balancing covariates is if you balance covariates, that can give you smaller confidence intervals, at least when the covariates are predictive of outcomes. So that is the intuitive, maybe that's really the message of this talk. That's what's well known. I'm going to give a way to balance covariates so that we can produce smaller confidence intervals when covariates predict outcomes. But I should tell you, there is no free lunch in this business. That's a theorem. Whatever you do that looks better under some assumptions, there's some other alternative universe where you're worse. I will make that theorem formal, but our goal is going to be to get smaller confidence intervals when the covariates predict outcomes with a worst case guarantee that we can never be much worse in distribution than a go-to design, like a uniform random assignment or a blocking design. Okay, so what they really needed was, I said, a distribution on assignments. So we generated 100 of them that all had low discrepancy, so they looked balanced, and they were all very different. Here I drew, I guess, 64 because that fits. But I don't want to tell you about what I did 4 years ago because at that time, well, they were starting the study in 3 weeks when they talked to me, and we didn't have much time to really figure out the right theory and the right algorithms. We just did something that seemed good enough. Now I know how to make this problem formal, which is what I'll tell you about in a few minutes, and tell you about the Gram-Schmidt walk and how it provides a very good algorithm for solving this problem. So first, let's just consider studies with two groups. Think of it as a test group and a control group, treatment and control. We're going to analyze studies under the Nyman-Rubin model, sometimes called the potential outcomes model for experiments. In this model, we assume that the assignment of individuals to treatment groups or subjects to treatment groups is the only source of randomness that we're going to rely on in our analysis. In particular, we're not going to view response to treatment as random. So if you put someone in the test or control group, we assume what happens to them is fixed based on that group. Now, you can consider other models. Some people like to view the response to treatment as random. If you do, that's basically okay. Just sample that randomness before you begin this analysis and everything will be fine. Okay, so we'll have two treatment groups, a test group and a control group, capital A and capital B. And we imagine that somewhere unknown to us are fixed potential outcomes. We observe little a of I, that's the outcome, if subject I is assigned to group A. And we observe little b of I if subject I is assigned to group B. But the key point is we can't observe both. No subject can be both the test and control group. That is what causes all of the trouble. When we talk about the design of an experiment, or when I talk about the design, I'm just talking about the distribution of the sets A and B, who is assigned to treatment and who's assigned to control. 3 natural designs to think of, which we mentioned in this talk. Well, one is uniform. You could actually just for each subject flip a coin. If it comes up heads, put them in group A, tails B, do it independently. This might be a little disconcerting if you have a small number of subjects, because some group could have you could get 0 elements in some group. A could be empty, or at least A and B could have different sizes. Sometimes you want the groups to be balanced and have the same size. So one way of doing that is you could choose a design uniformly at random. Like think of A being a uniform random subset of half of the subjects. Oh, and there's the matching design I mentioned earlier, where what you do is you take your subjects, you divide them into pairs, and for each you flip a coin. Say if it comes up heads, assign subject I to group A and J to B, or the other way around. Do that independently for each pair. All of these designs I just mentioned have the property that the expected size of A is half the elements, or the expected size of A is the same as the expected size of B. We're just assuming that for convenience, that's not necessary. You can adjust these designs to fix that, this one pretty much, and the designs I'll tell you about to get any sizes you want. I'm going to assume that what we want to measure, the go-to thing in this area, is what's called the average treatment effect. So outcomes, could be something like years added to life, something numerical. AI and BI should be real numbers. We want to measure the average of the difference over subjects I of what would happen if we put them in group A minus what would happen if we put them in group B. So that is really about the effect of the intervention we're doing. We call that average tau, and we will estimate it by tau hat, which is a very natural estimator. We're going to take the sum of the subjects in group A and measure their outcome, subtract off the corresponding sum for group B, And the normalizing coefficient is 2 over n. Now, I'm sure most of you have seen this, but just in case people haven't, I want to tell you where this comes from, because we'll use it again much later when we talk about confidence intervals. This is what's known as the Horvitz-Thompson estimator, where when you have a sum of things, but that you want to estimate, but you don't see them all, you only see them with some probability, what you do is for the ones you do observe, you scale them by multiplying by 1 over the probability you see them. This gives you the correct estimate in expectation. So in particular, the tau hat in expectation is equal to tau. And this is how you can see where the 2 over n comes from. Each item, like little a of I, we observe with probability 1/2 if I is in group capital A. So there's a 1/2 down there. Same with b of I, that gives you the 2 leading term to normalize. So this is the sort of estimator we will use. I want to mention, of course, there are other estimators you could use, some of which are very natural, which I'm not going to talk about, partially because they're just more complicated. One I'm not using that would be very reasonable is the difference of means. I could take the mean of A of I over group A and subtract the mean of B of I over group B. Now, if A and B have the exact same size, this is the same thing as the Horvitz-Thompson estimator. The designs we will construct, we can guarantee that A and B have very similar size, and I can still get theoretical guarantees. There's a section of our paper where we tell you how to guarantee they're the same size, and then some of our theoretical guarantees we don't establish. But the main reason I'm not using this when A and B can have different sizes is this is not even necessarily right in expectation. So it's much harder to reason about. But if someone wants to write a paper that can handle it, I will be very happy to read it, at least for these sorts of designs. Okay, of course, we're not happy just to get the expectation correct. We really care about how much error there is in our estimations. So to formulate the error algebraically, we'll write out a vector z, which tells you for each subject I which group they're in. Z will be 1 for the subjects in group A and -1 for the subjects in group B. We can now write the error as an inner product. The error, which is tau hat minus tau, well, I'll scale it by multiplying by n. We can write it as the inner product of z with this funny vector a plus b, where again, A was the vector of potential outcomes for group capital A, B was the vector of potential outcomes for group capital B. Actually, we add them together. And we're going to use this vector so much in the talk, more than A and B. We name it, and I call it mu. The error is 1 over n times the inner product of z with mu. Some people find this a little counterintuitive, so I included a proof, but I won't go over it. It is a routine calculation. I should also add, it's an artifact of this is because we are using a Horvitz-Thompson estimator, in case your intuition was bothered by this. So this tells us something already about why random designs are nice. The error is about the inner product of z with mu. If you were to just pick some z, like by solving an optimization problem in the covariates, like I was initially thinking of, that could go wrong. Because maybe z has a big inner product with mu. Like I know the covariates in advance. I don't know the potential outcomes. I don't know mu. If I pick z corresponding to some optimization, maybe these have a big inner product and we have large error, and that would be unfortunate. Okay, it seems unlikely, but I can't make that statement formal. So my statistically oriented friends are not happy with me saying it seems unlikely my algorithm will produce something correlated with mu. They want a distribution. And this is, of course, where randomness helps us, right? If we pick z to be a random ±1 vector in high dimensions, it's probably pretty darn close to being orthogonal to mu. Like the angle is usually very close to pi over 2. So that's the beginning of why random z is a good thing. It likely has a very small angle to mu. Let's try to make this a little more formal again. What we care about really is getting an estimate on the probability that tau hat differs from tau by some amount. I'm calling that T is my favorite parameter for measuring a threshold on the error. Now, we have standard ways that we measure this. And our hope is to be able to apply them to fancier designs than just independent random. The first go-to, and it's sort of the way I calibrate everything, is thinking about Chebyshev's inequality. We begin by estimating the variance of tau hat, which is the expectation of the square of the error, or scaled by 1 by n. Then, of course, once we know that, Chebyshev's inequality tells us the probability that the error is larger than any constant c times the variance, or square root of the variance of the standard deviation. That's the most 1 in c squared. That gets you some tail bounds. Usually we want stronger tail bounds. People often think about, normal random variables, and really we want tail bounds like you get from normal random variables, alternatively called Gaussian random variables, depending on which literature you're in. If we have a normal variable with mean 0 and variance sigma squared, we have very precise estimates on the probability that that variable is bigger than any value. If this is the Gaussian density, that probability is just the tail here, the integral under the curve. And while I don't know any nice closed form for it, I do have colleagues who you tell them standard values of t, and they can tell you to a few digits, what the complementary error function is. But we're going to work with something for which I do have a closed form and is a little bit easier to manipulate algebraically. That's the moment generating function. This is how we usually prove Chernoff bounds and Hoeffding bounds and things like that. So that is, for a random variable x, the expectation of the exponential of lambda x, where lambda is a parameter. So this you can think of as a transform where lambda is mapping to something. For a normal random variable, you get e to the sigma squared lambda squared over 2. And then you apply Markov's inequality. That gets you your tail bound. That tells you that the probability x is bigger than t is at most this. This is a bound that, okay, I like because it's easy to work with. I will admit it is great for a lot of theory. It is still pretty far from the correct tail bound in the regime that a lot of statisticians care about. That's something I hope someone can help us improve at some point. This is what we know how to work with. Okay, but I need to be a little more precise again, because there's no normal random variables in what I talked about so far. What we are going to instead do is we're going to work with the sub-Gaussian random variables, which intuitively you say that, say, a random variable sigma sub-Gaussian if it is at least as concentrated as a Gaussian. That's only intuitive. There are many approximately equivalent definitions where going from one different definition to another, you just lose a little bit on sigma. The most natural one corresponding to the tails would be to say the probability that x is more than, say, t times the standard deviation is at most what it is for a Gaussian. That would be natural. But we're going to work with the exponential moment generating function. So we will say that a random variable is sigma sub Gaussian if the exponential moment generating function is always less than what it would be for the corresponding Gaussian. When I was working on this, I had to learn a lot about sigma sub Gaussian random variables. So just so my go-to references, well, the one you should probably all go with is Philippe Rigolet's course and his notes. The other things I go with are Roman Verscheinen's book on the topic and Ramon van Handel's book, also based on his lecture notes. Okay, so the way we're going to get at tail bounds is through proving that certain quantities we care about are sigma sub Gaussian for a nice sigma. Oh, and I forgot to mention also we have, does it matter? Sure, maybe. Sometimes we want to deal with sub-Gaussian random vectors, where you say a vector is sigma sub Gaussian if whenever you take the inner product with any vector mu, say, then you get the appropriate sub-Gaussian real variable. So the appropriate scaling would be that it's sigma times the norm of mu sub Gaussian. And of course, random vectors of independent Gaussians are sigma sub Gaussian. Okay, now I've told you how we're going to measure concentration. Let's work out a formula for the variance of a general design, or at least the variance of tau hat. So the variance of tau hat It'll be scaled with a 1 and n squared in the front. That doesn't matter too much. Then we care about the expectation of the error. And recall the error is z transpose mu, where z was this vector that was plus or minus 1, depending on whether I is an A or B. Let's rewrite this square by writing it as a product of itself, but reversing where the transpose is each time, reversing the order of the terms. And then we get a very nice form for the variance. It looks like a quadratic form with mu on the outside and the expected outer product of z with itself on the inside. So this is a matrix. And we're going to use this matrix a lot. I'm going to give it a name. We'll call it capital Z. We want this variance to be small. And in our situation, we know Z, or we're really choosing Z. When we choose a design, we choose Z, but we don't know mu. So if I don't know mu and I know Z and I want this to be small, what I really want, the best I can do really is I try to minimize the largest eigenvalue of Z. In this case, Z is symmetric positive semi-definite. So same as minimizing the operator norm of Z. I want to make sure that for all mu, I could say I want maximum over mu of this Rayleigh quotient to be as small as possible. So let's see what happens in the IID case. If each entry of Z is chosen independently, little z that is, to be plus or minus 1, we can compute the matrix capital Z. The ij entry of the matrix capital Z is the expectation of little z of I times little z of j. When I is equal to j, these are the same. Both of them are 1 or minus 1. So this entry will definitely be 1 when I is equal to j. When I doesn't equal j, these are independent and mean 0. So their product is 0. That means that in the IID case, Z, this matrix is exactly the identity. And then we know exactly the variance of tau hat, our estimator. It's 1 and n squared times the squared norm of mu. This is, in some sense, optimal. If you give me any other design, you give me any other distribution on vectors little z, and you take a look at the matrix capital Z, its diagonals are all going to look like the identity. You're always going to have ones on the diagonal because z of I will always be equal to z of j when I is equal to j. That means that the largest eigenvalue of z is going to be at least 2. What that means is for any other z you choose, there has to exist some potential outcomes, some universe that give a vector mu where the variance is more than mu squared, or 1 over n times mu squared, the norm of mu squared. So if you don't pick the IID design, you know there's always going to be some mu on which you're worse. If you want to get lower variance, you need assumptions about mu. And what you can just hope is that if those assumptions fail, you don't get too much higher variance. So for example, let's take a look at a random balanced design where I make A and B of the same size. That means we're going to pick Z uniformly at random, subject to the fact that the sum of its entries is 0, and Z is plus or minus 1. We can now compute capital Z. The leading term is an n over n minus 1. There's an identity here. And then where it differs from before is here we subtract off a matrix, all of whose entries are 1 over n. So take all ones, divide by n. Since I like spectral graph theory, I just always think of this as a multiple of the Laplacian of the complete graph. That also, but yeah, you don't need to. Let's see what this means for the variance of the estimator. The lead term in the variance of tau hat when you use a balanced design is 1 over n minus 1 squared. So that's just a little bit worse than what we had from the IID design, because that had a 1 over n squared. This is a little bit bigger. The term that's smaller is this one. In the IID design, we had mu here, and we took its norm squared. Here, we take mu and we subtract off its average entry. So we take mu and we subtract off its mean. That's a projection orthogonal to the all ones vector. And it will be smaller. Well, it's always smaller than the norm of mu because it's a projection. And if the mean, if the average entry of mu is far from 0, then this will be much smaller than the norm of mu. So what you realize, this can be worse than the IID design, but it's often preferred because your mean entries might be wrong.
Then,
Or might
sorry.
not be 0. Yes.
So there is an interesting question in chat. Let me read it for you so that
Please.
you don't have to exit
Yeah, I
the
can't see
screen.
chat right now.
Yeah. So the question is this referring to this, the current design that you're talking about, is this a consequence of the Horwitz-Thompson estimator? That is, if you use difference in means estimator, then this design is better than the IID design?
Let's put it this way. Experimentally, on examples I have checked, yes, if you use our design, it will be better when you use difference of means than IID, and it should still be much better. So I don't think the quality of what we're observing is actually an artifact of using Horwitz-Thompson.
Mm-hmm.
It's just that Horwitz-Thompson is really easy to analyze, and our paper's 130 pages, so I think some simplification goes a long way here.
Okay.
And I'll admit, yeah, we don't know how to analyze the other ones yet, but we did a lot of simulations. By the way, if you look at our paper on arXiv, there are 2 versions. The simulations where we compare against difference of means is in the first version. And I'll explain a little why it's not in the second.
Okay, thanks.
Welcome. Again, if there are other questions, please interrupt, because 2 things. 1, I like questions. 2, I'm actually more articulate when I'm looking at people. I don't know why. Okay, so why would we prefer a balanced design? Well, imagine if A and B were non-negative or positive. If they're positive, then you know that the mean of mu is not going to be 0. And there's a darn good chance by subtracting off the mean here and projecting orthogonal to the all ones vector, you'll get lower variance. Okay, but the theme of this talk is the idea that we can balance covariates to improve precision and decrease error, at least if the covariates are correlated with outcomes. So let's make that algebraic. I will imagine we have a study with n subjects. Each of them has a vector of covariates. So we'll assume those vectors are in d dimensions. Those are the things we've measured about the subjects. We will arrange them into the columns of a matrix. I'll call the matrix capital X. And I claim that balancing covariates can help if this vector mu is close to the row span of X. Or I should say more precisely, it helps a lot if mu is close to the row span of X, even when it's a little bit close. Not orthogonal to, we can still get improvement. So to explain how to analyze this, let's first look at the ideal case when mu is actually in the row span of X. So I can write mu as X transpose beta, where beta is the coefficients that you need to multiply X by in order to get mu. If you plug this into our formula for the variance, instead of mu transpose z mu, you now have a different quadratic form with beta as a vector on the outside and a vector xz x transpose on the inside. Now we don't know beta. So if we don't know beta, and we don't have any assumptions about beta right now, the best we can try to do is make xz x transpose small in, let's say, operator norm largest eigenvalue. And then we can apply this nice upper bound that this quadratic form is at most the norm of beta squared times the 2 norm of the matrix xz x transpose. And I'll say I'm doing this in the ideal case now, where mu is in the span of X, but we'll handle the general case in a moment. But this is where I can motivate and tell you about the algorithm, the Gram-Schmidt walk of Bonsall, Dadeusz, Garg, Lovett. I should say.
So Dan, just quick comment again.
Mm-hmm.
So xz x transpose, is that what is suggesting then also the name balancing?
Yeah, you can think maybe. So z is right, this plus minus 1 vector, and right, I want this norm to be small, and that's really what I mean by balancing. Yes.
Yeah.
I do mean
often there's different type of row and column scaling procedures that people do for balancing, like to have different notions of balancing. This is one particular notion coming out of your model.
Right. Yes, this is one particular notion of balancing, and it is right. It is not, and let me just point out, this notion of balancing is really, so some people think about balancing like in standard discrepancy theory, you fix some vector z and you look at the covariates. This is sort of balancing on average in every direction. Mm-hmm. And for the same reason I said before with a random z and that inner product, it is possible to get much better balancing on average in every direction than you could really hope to get deterministically. Yes, so this is our notion of balance. And this is exactly what the Gram-Schmidt walk does.
Thanks.
Welcome. So the Gram-Schmidt walk of Bonsall, Dushkarg, and Lovett, it's a polynomial time algorithm, very efficient even, that if you give it as input vectors x1 through xn, and just to normalize, let's assume they have Euclidean norm at most 1, their algorithm chooses a random vector z in plus minus 1 to the n, so that the vector x times little z, that is, the sum of the vectors xi times the sum of the zi's, that is a root 40 sub-Gaussian random vector. Or that is equivalent to saying that this matrix we're looking at, XEX transpose, has a operator norm at most 40. The reason they did this is this enabled them to find an algorithm for a problem in discrepancy theory that called Banachuk's problem that can be viewed as another balancing problem that I won't describe. I will say that for their purposes, 40 was fine. They really were happy with any constant for their application. We were not. About a third of our paper is actually dedicated to showing that this constant is in fact 1. And so literally this is 1 sub-Gaussian, and that is optimal. You cannot possibly do better. No better guarantee exists. And the reason we really care about that is this number here goes into the width of your confidence interval. So if you're dealing with root 40 instead of 1, then your confidence intervals would be root 40 times as big. That means you don't get in the door of an experimentalist's office. I'll admit it took us a long time before we realized the number here was actually 1. Thankfully, their algorithm is not that hard to implement, so we could do a lot of tests and actually get a lot of experimental confidence before we prove it. And I will tell you a little bit, I think I'm going to have time, about how their algorithm works. But before I do that, I want to plug this into the analysis to see what the consequences are. So let's go back to our ideal case, where mu is in the span of x. First, let's just see what the variance is going to be. Well, now our variance is going to be like XEX transpose, that operator norm, that I've just told you can be at most 1, times the norm of beta squared. The key point I just want to point out is there are a lot of situations where the norm of beta squared is really much less than the norm of mu squared, which is what we would have had before with, say, an IID design. In particular, like here's just a simple model. You could see, what if the xi's were all unit vectors? Think of d as being much less than n. Then it's reasonable to think that the rows of x might be nearly orthogonal. If the rows of x were orthogonal, then the norm of beta squared will be smaller than the norm of mu squared by a factor d over n. So if d is much smaller than n, you can get much smaller variance in this ideal case. Let's see about in general. So in general, what I'm going to do is let beta represent the linear combination of the rows of x that comes closest to mu. And then let epsilon be the error. So epsilon is the part of mu not explained by the rows of the covariates. We can then again substitute this formula, mu is equal to epsilon plus x transpose beta, into our expression for the variance, and we get 3 terms. A quadratic form in z, which previously we had mu written there, now we have it in terms of epsilon. The quadratic form in XEX transpose with a beta, plus a cross term. Let's ignore that for now. It'll work out nicely. We can then try to upper bound this by maybe the 2 norm of z times the norm of epsilon squared, the 2 norm of XEX transpose times the 2 norm of beta squared, and then there's the cross term. And what you realize is you want both the 2 norm of z to be small and the 2 norm of XEX transpose to be small, or I should say operator norms. We want them both to be so. Well, you can't get them. Each of them we can say individually we can upper bound by 1. You can't simultaneously upper bound both by 1 in general. So what we actually have is a trade-off. So we call the Gram-Schmidt walk design, we specify by a trade-off parameter phi that should be between 0 and 1. And it tells you how much you care about error when you don't have a linear, when mu is not in the span of the covariates, and how much you care about when it is. I'll make that precise in a moment. But what we do is we run the Gram-Schmidt walk algorithm on this vector. So what we do is we take the xi's and we multiply them by the square root of 1 minus phi, and then we augment them. We put an elementary unit vector up top. And that vector is unique to each xi, multiplies it by root phi. So this is really our input matrix for the Gram-Schmidt walk. And I should say we also randomly permute the order of the vectors. That has nothing to do with the Gram-Schmidt walk, but it actually enables our confidence interval estimations at the end. Okay, so now let's see what the Gram-Schmidt walk guarantees. So the first two guarantees you can work out, and the ones we knew for a while, was that the 2 norm of z previously was, we could say it's at most 1. It's at most 1 over phi. So the IID design, you get 1. Here we say it's at most 1 over phi. The 2 norm of XEX transpose is at most 1 over 1 minus phi. Let's deal with the cross terms. They're going to come out beautifully once you realize that you can upper bound z in the order of positive semi-definite matrices. It's at most this matrix. Well, let's not dwell on the matrix. Let me tell you the consequence. It means that the variance of tau can be upper bounded by this nice expression. After the 1 over n squared, you minimize over beta. And you take a look at the squared norm of mu minus x transpose beta. So that's the term I called epsilon before. The difference between mu and the best linear approximation in the rows of x, but since that's a function of beta, I'm not writing it as epsilon here. You multiply that by 1 over phi. Here you multiply the squared norm of beta by 1 over 1 minus phi. And I should emphasize, this is just for analysis. One never performs this regression, like to adjust any covariates or anything. This is just an upper bound on the variance. And I should say we get the same sub-Gaussian tails you would expect. So once you have this variance, you can say actually it's a tau hat is actually a sub-Gaussian random variable with this variance. We get sub-Gaussian tails. Many of you will recognize expressions like this. This is really a ridge regression, or what we call regularized least squares. It's what you do when you want to minimize some least squares, but there's noise in your data. So you add on a penalty term in the coefficients. If you're not used to it, well, usually you're used to it with a coefficient of 1 out front. So you just got to scale it a little bit. Let me point out first that when mu is near the row span of x, this term is small. And this is small when phi is near 1, and this gets big when phi is near 1. So there's a trade-off between you have to choose phi in advance. I'm sorry, we're stuck with that. If you have some idea about how close mu might be to the span of the rows of x, then you can choose phi appropriately. There are other ways to think about the choice of phi. One thing I think about is imagine your number of subjects grows, or just think about d much smaller than n. This vector, epsilon, has one term for every subject. So this term grows with the number of subjects. This term does not in any reasonable model that you may choose. So if d is much less than n, and you don't have absurd, horrible outliers in your data, what you expect is this term to actually be relatively big compared to that one. In which case, what you want to do is you want phi to be very close to 1. And I like choosing phi very close to 1, maybe like 1.1, because, sorry, 0.9 has to be 0.1. Then you can make an assertion that your variance will be low if mu is close to the row span of x, but you can't be more than 1 over phi as bad as you would get with the IID design, regardless of mu. So you can gain when your assumption you want holds. You can never lose too much, no matter how conspiratorial your universe is. Okay, that's what I want to say about the guarantees. I would like to tell you a little bit about the Gram-Schmidt walk algorithm. And then I think I have time to tell you a little bit about confidence intervals. So remember, the Gram-Schmidt walk algorithm is how we choose this vector z of plus minus 1 entries. And the way they choose it is by an iterative process, somewhat modeled on Gram-Schmidt orthogonalization. It starts with z being equal to the all zero vector. And over the course of the algorithm, z will change. All the entries change basically at every step. they maintain the condition that Z is always in -1, 1 to the n. So all the entries will always have absolute value at most 1. Actually, what will happen is that every single step, some entry that wasn't 1 or -1 will become 1 or -1. So it's really just a while loop. You begin, so while there's some entry that's not 1 or -1, we're going to do an update. The way we do the update is we have to pick an update direction. I'll tell you briefly how in a moment. We'll call it U. And then what you do is you add, we don't really add mu to Z. You pick a random variable delta with expectation 0 and add delta times mu to Z. And you pick the distribution on delta so that you have to fix one coordinate to plus or -1, and the others stay in -1, 1. And I will say ideally, because it's not true throughout the algorithm, but in many steps, really what you want is that if I take a look at the update U and multiply by X, that should be orthogonal to X times Z. That's at least the first way to think about the algorithm. You eventually understand it doesn't always hold, but all of your intuition goes through if it does. Okay, so here's how we describe it. We want to fix entries to 1 or -1. Those that are not 1, once they get to 1 or -1, they are fixed. Frozen, you could say. The others we call active. In the algorithm, at every iteration, they choose what's called a pivot. That is the largest active entry. Could have gone with the smallest. You just need to fix an order. And the way the update vector is chosen is so that its entry is 1 on the pivot. It is 0 on all of the non-active elements. It's 0 on everything that's frozen. So that means the update vector will not change any entry that was already 1 or -1. And there's an orthogonality condition. X times the update vector should be orthogonal to all of the xi's. Those are the columns, the covariate vectors, for the remaining active entries. And if you look at this, you will observe that this is going to be, you're going to have one more variable than constraints. I've written basically a bunch of linear equations. There will be one more variable. So there's always a non-zero solution. And that's how they get their vector U. And to make this efficient, you do it with rank 1 updates. And then as I say, you just need to pick a distribution on delta so that the expectation is 0. And when you add delta times mu, you know you will fix one coordinate. And I guess I can just say that means that delta takes one of 2 values, a positive value or a negative value, and you can figure out what they are. And once you figure out what the positive values are and the negative values that keep everything in 1 -1 and fix some entry to 1 or -1, you get the distribution. Okay, let me skip telling you about the walk or the analysis, other than to say that it's sort of a martingale. One question you might ask is, can you improve the Gram-Schmidt walk algorithm? I mean, I told you no, but let me tell you why, and I'll say that in 2 senses. One, there isn't much room to improve on the variance. If you take a look at XEX transpose, or that's the expectation of the outer product of XZ with itself, we're looking at the operator norm, we prove that's at most 1. That implies that if I look at the trace of the expectation of XZ, outer product with itself, that's at most D. And that's exactly equal to the expectation of the squared norm of XZ. And you can't hope for that to be less than D. I mean, think, what if X is like just an identity with a bunch of zeros? And if Z is plus or minus 1, so now, I take some plus or minus 1 vector, I multiply it by this, these entries get zeroed out. I'm going to get D entries that are plus or minus 1. That's going to have norm squared D. You're stuck. So you can't improve this. If you don't like having a bunch of zeros there, just like take a couple of odd copies of the identity, an odd number of them, you'll get the same thing. Okay, that means you can't in general get a better guarantee. You might also wonder, given some particular matrix of covariates, can you do better? Because it could be that your covariates are nicer than like this thing with the identities. Well, Charikar, Newman, and Nikolov proved that that's NP-hard, at least to do much better. They proved that it's actually NP-hard to distinguish 2 simple cases. One where there's a plus or minus 1 vector, Z, such that XZ is the all 0. That's hard to distinguish from the case where for all plus or minus 1 vectors Z, the 2 norm is at least CD for some constant C. So the C is not necessarily 1, but it means at least it's NP-hard to improve this too much. Now, again, maybe there are very special structures of covariate vectors where you can do better, but I don't know how to begin defining them. Okay, let me finish by telling you about confidence intervals. It isn't enough to know that the variance is small. At the end of an experiment, people have to compute a confidence interval. So here's a way to at least compute a conservative confidence interval. We want an upper bound on the variance that is right. And we use the fact that we had this variance is at most this matrix, this quadratic form in some funny matrix we'll call Q. What we need to do is we need to estimate an upper bound on mu transpose Q mu. And we can do that by now expanding mu. It's a quadratic form in A, a quadratic form in B, and a quadratic form in 2 A transpose QB. And we can estimate A transpose QA using a Horvitz-Thompson estimator. Think about what this is. If we expand this, it's the sum over Qij's times A of I times A of J. So what we do is we just weight the terms by the probability we observe them. You take the sum and you divide each term by probability I and J are in A. This breaks down when you go to the term A transpose QB, because one of the annoying terms that comes up here corresponds to the case where I is equal to J. And in that case, when I is equal to J, it is never the case that I is in A and I is in B, right? Each subject can only get assigned to group A or group B. They can't be assigned to both. You get a 0. So this looks like a problem, but it's not so bad. Apparently, the solution to this goes back to a 1923 paper of Nyman, where you just shift some diagonals of Q. So let D be the diagonal of Q and use this classic inequality. Well, we usually say it's 2AB is at most A squared plus B squared. Diagonalizing, it's 2A transpose DB is at most A transpose DA plus B transpose DB. Rewrite this by shifting the diagonals and we get an upper bound. With Q, we get a quadratic form in Q plus D, another one in Q plus D, and the one in Q minus D, and the bad term goes away. So this will be a slight overestimate of variance. Although there is another problem I should add. I sort of glossed over before that in order for this to work, we need none of those denominators to be 0. I was upset about one that I knew was 0, but we need to know that all these pairwise inclusion probabilities are bigger than 0. And the Gram-Schmidt walk was not designed for that. We prove a result that says they're not 0. I'd like a better result. We prove at least that if you randomly permute the vectors, then we get a lower bound on all of these probabilities. Let me not go into the proof, basically using a bunch of linear algebra and a martingale fact. I think something better is true, but really we want a better bound. At least I will say in practice, what you would do is just choose your design and sample and you can compute these probabilities. And if one of them came out to be really close to 0, then you probably don't want to use our design. So, there we go. That takes me to talking about in practice. In practice, like the study I was talking about at first, that was a $10 million study. So you can afford to spend a couple $1,000s of compute time simulating every design you could possibly think of using and decide which one you want to use. And that's the sort of thing I think would make sense. In this case, we proved this design is okay, but really you would estimate those probabilities. You don't just have to include the covariates. You can include functions of covariates. You can weight the covariates like we did. One thing you might ask is, can you use some sort of machine learning or regression when you're done to look at the outcomes and look at the covariates and then adjust tau hat? And my answer is you can. Many people do, but I urge caution because you know the expectation of your estimator, or there's no reason to believe it'll come out right. And usually when you do this, you are making assumptions. And if your assumptions are right, all is nice. But if your assumptions are wrong, you can make your estimators really bad. And for any legitimate study, you should be pre-registering your analysis techniques. Like, you got to be careful you're not overfitting once you start doing that. And at least, I just want to remind you, we are doing that implicitly, solely in the choice of the design. There is a ridge regression going on here. But because we're using the Horvitz-Thompson estimator at the end, you can't mess up your estimates too much. Okay, other open questions. You can consider other structures of relationships between X and mu, and we should. Can you get smaller confidence intervals? Again, we want to improve the way we get those, or maybe someone else will. The trade-off between the two norm of z and x transpose, x dx transpose we get is within a constant of optimal, but not necessarily optimal. You could try to tighten it. It's getting that constant right is good. What we've been working on for the last year is the online version, where your subjects come into the study one at a time. And at that point, you need to assign them to treatment or control. We think we know how to solve that. We'll see if the proofs work out. And if you want to learn more, well, our paper is an archive. There are packages you can get on GitHub to implement it, both in Julia and R. As I said, there are two versions of the paper. The first was a very computer sciencey style exposition. The second one has more results, but we also attempted to write it for experimentalists and statisticians. So it has more results, but different simulations. Thank you. And I'm happy to take questions if y'all still have time.
Thanks, Dan. So floor is open for some questions. So whoever has a question, just go right ahead. Looks like Ali has a question.
Yes, thank you very much, Dan, for a wonderful talk. Had a quick question. Given that the variance is bounded by that expression that you get for the T1 of regularized least square or the ridge regression, I wonder if there's another interpretation related to sort of stochastic robust least square, where, because there's a way, if you go one slide back, there's a way to derive that ridge regression, the purple text.
Yes, there we go, yeah.
Yes, so one can think of this as, a random X transpose where the part that you have in here is the mean,
yes,
and the part that is related to its variance that is related to the fees. And I wonder if that interpretation may...
So I don't know, honestly. I haven't been thinking about X at all random, in part because it's the covariates when we measure them. And my co-author, Frederick, who is really an expert in experimental design, I was very interested to discover that's one of the main things they do in the Yale Political Science Department. We have a number of experts on experimental design, but he hates random models and doesn't like to think about what would happen with a random X. He likes to just think, we've measured X, now we've got to deal with it. And I will admit, in different studies, you get very different sorts of X's. So we just haven't gone down that route. But I know that there are a lot of different literatures in experimental design where people like to deal with models like that. And if someone understands them, I would welcome seeing if our results make sense in that context.
I guess I was thinking that because one interpretation of Tikhonov of regularization is precisely that you have an X that it's centered around matrix X, but there's some randomness that relates to your phi. By adjusting phi, you're adjusting that randomness somehow.
It's true. Yeah. So I don't have an interpretation in that form.
Okay.
I'm sorry to say.
Thank you very much.
Okay.
Do we have any other question? Time for like a couple of questions before. Okay, I have some other, I have just a slight kind of computational question, Dan, that I had. Is even though computation is not a concern, I'm just curious, because it's called this, whatever, Gram-Schmidt walk, what kind of running time does it really have?
So in the original algorithm, you'd get time, let me get this straight here. It should be about n cubed, like Gram-Schmidt. It turns out that you can actually, if you care about the time in terms of n and d, oddly enough, so in this augmented case, we can get it down to n squared d.
Okay.
And that's fast enough that we run it on the biggest examples you'll get pretty quickly. I still suspect it could be nd squared, but I don't know that it would actually make that much of a difference unless you're doing like some Amazon scale experiment on customers or something.
Yeah. I was just curious to understand that, and also to see if you thought of potentially an alternative way to view that randomized algorithm that is the Gram-Schmidt walk.
So yes, so one of the things we've been doing, well, okay, maybe I don't have an alternative way to view it.
But to
And by
analyze
the way,
it.
if you look at the talks by the authors on it, they give a very nice explanation of where
Okay.
it comes from. I remember seeing a talk at Stock a few years back, and I just wanted to apply the thing. And I was actually very happily surprised to discover I could, but it was an accident a few years later. We have been working on other algorithms that give the same guarantee. So like I do have two contenders, one of them that seems to work online, one which is has a nice closed form description of the distribution.
Right, because at least in the story you told today, means of course I won't remember everything. A priori, you wouldn't kind of imagine that somehow this method should do the job.
No, you wouldn't have. And we tried many others, and we even had others that could get us to a constant.
Mm-hmm.
Because we didn't realize this was going to be a constant because they published root 40. And when you look at the proof, it's not clear how it would go away. So it's actually a good, darn good thing we did some experiments and observed that, like, you know, I used every technique known in black box optimization to try to find a matrix X that would actually make that operator norm more than one and could not find it.
Mm-hmm.
So we eventually decided to try proving it. But we were not optimistic at first.
Very impressive.
Do we have time for another question?
Kind of out of time, but sure, we can have one more question. Those who want to exit could exit whenever for the sake of, you know, if they have other things to do. But I'm curious if there's another question anybody has.
And now the great thing about Zoom is you don't even knock over someone's coffee as you get up to leave a lecture from the middle of the
Right.
break. And the lecturer can't tell.
I guess my question was, can you say a few words of the authors of that article that described
Yeah.
what were they using it for?
So they were using it for something called Banachik's theorem. So Banachik's theorem says that if you have a convex body with at least some lower bound on the Gaussian measure, it has to be at least a half.
Mm-hmm.
And you give me a bunch of unit vectors, then there is a plus or minus one combination. You want to say there's a plus or minus one sum of them that lies inside the convex body. That is not quite true, but they say there's a sum of them that lies within 5 times the convex body. So this is in line of a bunch of work really started by Nikhil Bansal a decade ago on showing that there were a bunch of existence results in discrepancy theory that we could make algorithmically efficient. He first famously started with Spencer's algorithm. Mm-hmm. From Spencer's famous 6 standard deviations suffice, and came up with an algorithm for that. And many people thought there was no polynomial time algorithm before Bansal's work. Right. And now since then, there's a huge number of discrepancy theorems where we have polynomial time algorithms. And you know, the one, of course, I really want to see is a polynomial time algorithm for Caddis and Singer, but busted my head against that a lot. And it's going to clearly take someone else's ideas. And this algorithm doesn't seem to do it. I assure you we've tried.
Don't waste your time.
Oh, I try everything. As I said, that's why I can make assertions about using every black box optimization routine known to mankind. It's how I find counterexamples to algorithms.
Great. Thank you very much.
Thanks, Dan.
Thank you. And I hope to see all of you in Boston, you know, a couple of months from now when we can travel again.
Yes. Definitely. Thanks, Dan.
Okay, bye.
Bye.